Hello everybody, here we are at the end of the lecture series, and this is the last lecture of this course, Optimal Control Guidance Estimation. So, last two lectures, as I told in the previous lecture, we are reviewing this material what we have covered in rest of the 38 lectures actually, and then lecture 39, just the previous lecture we summarized many things up to LQR theory and SDRE also. So, let us continue that series and then kind of quickly review the rest of the material as well. So, next topic that we discussed is something called dynamic programming, and this was kind of motivated with the objective that we want to have state feedback optimal control solution really. Okay, open loop sort of things we are not happy anymore. And then there is a fundamental theorem of optimal control which tells us that any part of the optimal trajectory is also an optimal trajectory, and that was that we explained this way, that if it happens that A to B and via C, if we claim that this path is optimal, the colored solid one, and then if there is something like a non-optimal path from A to C, it is not going to happen, because in that case then this path A to C via dotted line and then C to B would have been the optimal path actually. But by definition we are telling that okay, from the to begin with this path is optimal and hence this is not allowed. That means if we confine our problem from A to C, then this is also going to be an optimal by its own way actually. Okay. So, that means any part of the optimal trajectory is actually an optimal trajectory, and using that and expanding the cost function for something like cost to go and things like that, we came up with this optimal control problem formulation and an associated solution like this. We started with minimizing this cost function. There is no terminal penalty, remember that, subject to this nonlinear state equation with initial condition and final conditions like this, where U now happens to be kind of an admissible set. Okay, so where it cannot be arbitrary, but it must belong to something like an admissible set actually. Okay, which can be infinity. Which can be infinite depending on the situation actually. Then after the analysis, we will end up with this formulation that if you define something called optimal cost, that means this cost function is evaluated on using optimal control trajectory as well as optimal state trajectory, then that we define as optimal cost, and this optimal cost must satisfy this equation which is famously called as Jacobi equation, that means Hamilton-Jacobi-Bellman equation actually. Okay. So, this Hamilton-Jacobi-Bellman equation, you can see that this Hamiltonian is not any Hamiltonian, but this Hamiltonian is optimal Hamiltonian actually, which this Hamiltonian evaluated on the optimal path actually. Okay. And on the way Hamiltonian takes lambda also, and lambda happens to be del v by del x here, and then you can see that h opt is a function of lambda and lambda is a del v by del x. That means this equation is essentially a nonlinear partial differential equation actually. Okay. So, that was the observation. And to get the further observation is if omega is infinite, that means there is no control bound per se, then h opt can be computed by computing this standard thing del s by del e equal to 0. Otherwise, you have to account for this control bound and then find a solution actually. Okay. Alright. So, now we can tell, okay, if you consider that T f is fixed, okay, then v of T f x f, the integral happens to be from T f to T f, that means integral is 0 actually. Okay, so that will give us a boundary condition. Now, if there is a terminal penalty also, the integral part will become 0, but v of T of x f will be phi of T of x f. So, that is the only change. The Jacobi equation remains same. The boundary condition happens to be instead of 0, okay, it will happen to be the same function evaluated at x f actually. And there is another observation that if T f goes to infinity, then del v by del t is 0. So, we have only that part of the equation which is coming from h opt equal to 0. But still remember, it is still a partial differential equation because lambda is a vector valued function del v by del x actually. Okay, if it is a scalar problem, then only it becomes something like a ODE problem after that actually. Okay. Alright, so this is how it is. Then some facts also we studied on the way, that dynamic programming is essentially a powerful technique in the sense that if the Jacobi equation is solved, then it essentially leads to state feedback form of optimal control solution. The second is Jacobi equation is both necessary and sufficient for the optimal control function. That means for the optimal control problem, we do not have to really once we solve for Jacobi or we demonstrate that some solution satisfies Jacobi equation, then it is both necessary and sufficient conditions are done actually. Then you also saw that even though the Hajjavi equation is a nonlinear PDE, essentially it means it can have multiple solutions. Then it tells this result tells us that at least one of the control solution that results from the solution of Hajjavi equation is guaranteed to be stabilizing. So we have a finite set of solutions, out of which we will be able to select one stabilizing solution at least, and that will be our optimal control solution also basically. Okay. But there are difficulties also that the resulting PDE of the Hajjavi equation is extremely difficult to solve in general, and if you really run into this numerical way of solving this, then it runs into this huge computational storage and requirement, and to the extent that these modern computers are also not useful, it runs into the computational complexity problems and all that actually. So this is essentially called as curse of dimensionality, which the terminology Wellman himself defined that. Okay. Which means that if the control duration of control application duration is longer, or the number of states are higher, the dimension of state vector is higher, then we these problems, I mean the computational requirement grows exponentially actually. So that is not possible in general. Alright, so to avoid that, there are recent ideas called approximate dynamic programming, and then this formulation in discrete time framework, where the cost function happens to be like this, and then the state equation is in discrete domain, xk plus 1 happens to be like this actually. Then we write it in a very similar way that we wrote for dynamic programming sense. And the cost to go from time tk can be written something like utility function at time tk plus cost to go from time tk plus 1. Then defining lambda k something like del j by del xk, okay, and the optimal control equation that needs to be satisfied is del jk by del uk equal to 0. And this leads to this condition that this expression has to be 0. Okay. Now remember lambda k plus 1 is coming now here. Okay. And similarly, the co-state equation, if you analyze, it turns out to be like a long expression, but on the optimal path this is 0, and hence this expression is 0. So we will end up with only that actually. So this is the co-state equation on optimal path actually. Okay. So essentially we will end up with again the state equation, co-state equation, optimal control equation, boundary condition, things like that. So even though we started with this dynamic programming ideas, we actually ended up with this Hamiltonian sort of a formulation of necessary conditions, where we had the state, co-state, optimal control equation essentially. Alright, so this is why using this we also talk something like adaptive critique and single network adaptive critique designs on how do you make use of this approximate dynamic programming results actually. Okay. Now the philosophy was like this: we have two neural networks. One takes the input xk and gives the output uk. The other takes the input xk and gives the output lambda k actually. So now after mutually consistent training, eventually this action network will capture the function, the optimal control function that lies between xk and uk. And hence after successful training, we can keep using this, which will produce the optimal control relationship as a function of xk actually. So that was the idea there. So the action network leads to the optimal control solution after, of course, mutual consistent training of both the networks actually. So there are advantages. First advantage was it is applicable to nonlinear problems in general, and that doesn't require any approximation like linear or quasi-linear like that. You don't need any of that. The second is it actually is possible, the solution is valid directly for a large number of initial conditions. Essentially it leads to this feedback optimal control in the domain of interest actually. Then it gives some sort of like a computational load sense. It is feasible because you don't really run into this huge computational requirement running into months and years actually. Here it is possible to do that in a few minutes or maximum like 10, 20, half an hour or like that actually. So it is feasible computational load even for neural network training. Remember, after training, it's just an evaluation of a closed form expression. So that is, that is certainly possible to use it in real time actually. But even during training, it doesn't take too much of time. It takes maximum about, I'll put something like 20-30 minutes actually to train a network actually. Okay. Then it's a self-contained methodology. It doesn't talk about relying on others and all that actually. And essentially, it's possible to use it for real-time control application, because ultimately after training, all that it's evaluation of something like a closed form expression from the sector utilizing this trained neural network weights actually. Okay. is a closed form function of xk actually. So that is possible to do online computation basically. Okay. Now, how do you do this synthesis? We came up with this structure actually. We assume that while X1 network training, the critic network is optimal and vice versa. So, while X1 network training, we randomly select xk and then pass it through X1 network that way. You get uk. Utilizing xk and uk in the state equation, we get xk plus 1. Utilizing that in the critic network, which is assumed to be optimal, you get lambda k plus 1. And again, utilizing this xk and lambda k plus 1, you get the desired uk star. So, now remember, out of these three conditions, state, co-state and optimal control, we have actually used state equation and optimal control equation while training the X1 network. So, now this is the actual UK, whereas this U star k is the desired UK. Now, if these two are very close to each other, essentially the difference if you do and then take the norm, it should be small number. If it is they are close to each other, okay, then you stop. Okay, that means the X1 network is trained already. If not, you keep training. I mean, in other words, take this as input and take that as output, the desired output, and then adjust the weights, and then repeat the cycle with respect to a different set of xk's actually. Okay. And these trainings are typically done in batch mode training, where you don't use only one particular xk, but generate a bunch of xk, let's say 100 xk's together and things like that actually. Okay. Now, going back to the critic training, the structure is something like this. Here, you are assuming that X1 network is optimal, and the critic network at the next time step ahead is also optimal, and that is justified because the boundary condition, if you see in co-state, that is given at the final time actually. So, if you come from that side of the story, it tells that okay, I will start from t equal to tf, I mean the close proximity to 0 basically in regulator problems. And then utilizing these two philosophies, that X1 network is optimal and critic network is also optimal for future time basically. Then I can come up with this algorithm, I mean this idea of training this. I start with a set of xk's randomly selected again and get my actual lambdas, but the same xk's can be used in X1 network and then get uk, and once xk is also there and uk is also there, I can use that in state equation, get xk plus 1, then use that in critic equation, critic network, get lambda k plus 1. And utilizing xk and lambda k plus 1, I will get the desired lambda k actually. So, if these two are close, I will not train it, the network is already optimal. If not, I will try this as input and that is output and train it actually. So, I will keep on doing that and then go back to X1 network training, come to critic network training and things like that. Ultimately, when there is no cycle training improvement, then we assume that the training is consistent, and then we tell okay, whatever converge network from there, that gives us the optimal control for that particular plant actually. So, but moving on, we also had this single network adaptive critic design, where it told okay, wait a second, we don't really have to do two networks for all type of problems. For a class of problems where the optimal control equation is explicitly solvable or symbolically solvable for control in terms of state and co-state, all that I need to know is to get my lambda k plus 1. Once xk is known and somehow I get lambda k plus 1, then I can utilize this closed form solution that is available with me to evaluate my uk. So, I really don't need to have X1 network training as a part of the training procedure actually. So, that the advantages, it retains all the advantages of adaptive critic synthesis, essentially eliminates the X1 network and also eliminates the iterative training between X1 and critic actually. So, that is also gone there actually. Okay. So, this leads to several improvements, especially it saves a lot of computational time even for offline training actually. It also eliminates approximations involved in the in the X1 network, because that is no more required, and because X1 network is also not required, the cycle training is also not required. So, all that you do is one set of training for the critic network and you are done actually. Okay. So, that is the idea of single network adaptive critic. How do you do it? All the three necessary conditions are used in this setting. You take xk and get lambda k plus 1, and you use both xk and lambda k plus 1, get uk. Now, you can use xk and uk to get xk plus 1. Once you have xk plus 1, you can get lambda k plus 2, assuming the critic network is optimal for the future time. And then xk plus 1 and lambda k plus 2, if you use in co-state equation, you get desired lambda k plus 1 actually. So, again, if these two are close, don't train, training is already done. If not, then you train this network again in a batch training sense actually. Alright, so here you can see the optimal control, state equation and co-state, all three are actually getting used, and by using this structure we are also using this boundary condition actually, because in the future time we are assuming the critical network is optimal, and that is guaranteed by first training the network using the boundary condition actually. Okay. So, it starts with the boundary condition that the lambda of Tf whatever the del phi by del xn for finite time or infinite time problems, that lambda of Tf goes to 0, but the state also is close to 0. That means, if you start with very small numbers around 0 and then the corresponding lambdas should also be close to 0 actually. Okay. That means, LQR solution is valid in that sense. So, utilizing that LQR solution, if you pre-train the network properly, then the boundary condition is enforced actually in this network. So, that validates that justification comes from that side actually. Okay. So, alright. So, this is how it is done, and if it is not close to each other, again keep training and keep validating. So, that is how the network training proceeds actually. Then we moved on, and we also had a glimpse of what is called a transcription method that people have solved it. And the philosophy turns out to be something very close to static optimization really. So, what is this idea tells us is something like this. We convert the dynamic system variables into a finite set of static variables, or what we call as parameters now, and pose an equivalent static optimization problem. Okay. And solve this static optimization problem using this various static or parameter optimization methods using nonlinear programming techniques actually. Okay, so the variety of methods available in the literature which you can excite now, and then solve this. Okay, then go ahead actually getting that. Then assess the accuracy and then repeat the steps if necessary. Now the question is, how do you pose a static optimization problem? Depends on a variety of ways actually. Then we started with the idea of finite difference, and then we can use this Euler integration method formula, and then set up grid point solutions and all that we came up with for the state equation. And for the cost function, we can thought, okay, we will take trapezoidal rule, something like that, where we can actually discretize the cost function as well actually. So, now but at every grid point, every node point or every grid point, the state equation is satisfied as a kind of a algebraic constraint of variables actually. So, if you see that for better accuracy, you need lot of grid points actually. And then if you have lot of grid points, then essentially it leads up this high dimensional optimization problem, which has its own difficulties actually. Okay. So, this kind of issues which comes to comes to focus actually, then people have used something like sparse algebra, or then start with something like grid refinement, and then variety of ideas there, where you start with coarse grid, and then once you get a converse solution for that, refine the grids and again start solving it and things like that. That is grid refinement. And then we have this sparse matrix algebra, where you can eliminate this algebra around a lot of zeros actually. So, by using that, people have come up with somewhat efficient algorithms, but still I think they are not suitable for online sort of applications, where you really need very fast computation actually. But then we had this glimpse of this evolving method called pseudospectral transcription, which holds a lot of promise in my view actually. And that the idea was something like this. So, we wanted to have a very generic formulation, where you want to minimize this generic cost function with this terminal penalty and path penalty, subject to this cost function, and with endpoint conditions, both equality sense as well as path constraints in the inequality sense. The whole idea is to have an equivalent discretized formulation using this so-called pseudospectral discretization. But essentially the idea here is to convert the problem into a lower dimensional nonlinear programming problem. The dimensionality of the problem should not grow actually. Okay, we should be able to do the job with a very less number of grid points actually. And then we are not interested in sparse matrix formulation sort of thing. Essentially it can lead to dense matrix actually, dense matrix algebra basically. So, it is lower dimensional, but we do not waste our computation by having a sparse matrix formulation sort of thing actually. So, that was the whole idea. How do we go further? And people have come up with various things for last, and probably about from 2000 onwards, it has gained quite a bit of momentum actually. So, one idea is like this. We can start something like this. You can have a control parameterization in the form of basis functions, typically Chebyshev polynomials, Legendre polynomials like that. And control also can be parameterized. Sometimes people tell, okay, control need not be parameterized, because if you parameterize as part of this continuous function sort of thing, then essentially this discrete controls cannot be approximated. Okay, so if you want to have that kind of generalization with control bounds and all that, then probably that is not a very good idea. But that's not the point. The point here is to see the philosophy actually. So we have this we can start with control, state being approximated that way and control being approximated that way with a set of basis functions actually. Now we have to select a set of grid points, and how are these grid points selected and all sort of things are questions that has to be addressed actually. But the whole idea here is we have to discretize the state equation and cost function utilizing this thing as well as the system dynamics, and then we formulate this low dimensional nonlinear programming problem actually. Alright, so selection of grid points, there is something called collocation points also. Okay, so they are the points such that it satisfies the state equation exactly at these points actually. So they are called collocation points or simply called grid points actually. And there are ideas like, okay, what kind of grid points you want to select, because uniform grid points are no more good actually for this kind of things. So one idea is to have, if you select uniform thing, then if you see free endpoints, one fixed endpoint, arbitrary endpoints, none of the boundary conditions will get satisfied there actually. But slowly you can see Gauss Gauss collocation points or Gauss-Radov or Gauss-Lobatov like that, those are available in literature now. And increasing generality and satisfying all the boundary conditions of a variety of things. Now the universal recommendation is something like Gauss-Lobatov points actually. Okay, so we can select something like this, then proceed further with the further algebra like that. It essentially is a non-uniform grid point set, okay, where the problem dimensionality gets reduced quite a lot actually, and it satisfies the boundary conditions well also basically that way. Alright, now coming back, we have these approximations. So the state equation constraints, once you start something like this, and then we are interested in that, we can substitute x dot as something like x hat dot, and then see, okay, this x hat dot coming from this expression takes the form of something like this, where because this phi n of t is essentially a function of time, but it's an explicit function of time. So phi dot of t is essentially a number once evaluated at any grid point actually. Okay, that is actually phi n dot of t is an expression of time, explicit expression of time, and hence I can evaluate that at any point of time to get a number for phi n dot actually. Okay. Similarly, on the right hand side, wherever x is there, I will replace that with x hat. So this expression comes here. Wherever u is there, I will replace that with u. This u hat, this expression comes actually. Now multiply both sides with this delta function. Situated at Tn. Then you can essentially are telling that evaluate this now phi n t at that particular grid point. So that becomes a number now, and all these things become a number in the right hand side also. So essentially this actually tells us now a algebraic constraint, because this has become a number, no more a differential equation form and all that actually. Okay. So once it becomes a number, this is actually a constraint equation in the form of coefficients n and vn actually. Okay, that is how it results in algebraic constraints starting from the state equation actually. Now coming to the cost function, again similar thing can be done, but the ideas like something like quadrature rule and all that, where this cost functions can be evaluated in a much better accuracy sense basically actually. So that can also be discretized in that form. Now this utilizing this constraint, algebraic constraint and this discretized cost function, we have a parameterized cost formulation, in other words static optimization problem actually. So go ahead and solve it, this static optimization problem. And essentially it leads to this lower dimensional nonlinear programming problem, and hence it is computationally efficient actually. And there are variety of application problems, variety of convergence guarantees, variety of analysis tools, generalization, practical problems, everything is available over last 10 years in a variety of literature actually. Alright. Okay, then we moved on to this idea of MPSP, Model Predictive Static Programming Design, where we started with some problem formulation like this. We had this system dynamics and this output equation. So if we discretize that, it takes this form. And the idea was that t equal to tf, that means k equal to n. Our objective was this output yn should go to a particular set yn star, the particular values actually. Okay. That means if I take this error delta yn, that should go to 0 basically. Now this essentially leads us to this constraint formulation. Okay, if you start with a guess history, okay, and try to evaluate this, and then finally to see why this comes, because at every grid point I made some error in the control, and then I tell that as du1, du2 and all that, those are errors over my previous guess history, then essentially it leads to this kind of a formulation where this linear sort of constraint comes into picture. And if I want to minimize the quadratic cost function, I can write it that way. Okay, and essentially starts from tk, actually tk is my current time in that sense. And then we have the standard quadratic cost function with linear constraints actually. So it is possible to solve this in closed form actually. Now the question here is, the point to observe here is, this is a static equation, it is not a dynamic equation, and the dimensionality of this equation is also small actually. Okay, it's not state dimension happens to be much more than the output dimension actually. So that essentially tells us that essentially this is actually nothing but a parameter optimization problem, where the constant alpha, constant lambda, okay, will do the job. We don't really need to have a dynamically varying lambda basically. Okay. So that essentially leads, and not only that, utilizing that we can also get a closed form solution for this errors in the control, and so that the iteration can proceed faster. And on the way we have to compute this sensitivity matrices also, but that can be computed recursively as well. So because of all this, it leads to a very fast computation essentially, and hence it is we think that it is possible to kind of utilize for online applications essentially. Alright, so necessary conditions of this is actually a static optimization problem. So the very standard way of approaching that is to formulate an augmented cost function and then utilize this, use these necessary conditions of optimality. Essentially this partial derivatives needs to be 0. So solve these two equations, and then that can be and then arrive at this kind of a control update formula utilizing this lambda structures, and lambda can be given something like this, where a lambda and v lambda can be computed that way actually. Also somebody wants to have a finite number of iterations at any grid point, then this idea of iteration unfolding can be excited there actually. Alright, so there are reasons for this computational efficiency, and I have told many of that. So this costed variable becomes static, and that is the major point actually. Then the dimension of the costed vector is also small. The costed vector actually can be computed symbolically in closed form solution, and then this computation of this recursive matrices, computation of sensitivity matrices can be done recursively. So because of this method happens to be computationally quite efficient actually. Then we thought of extending this idea to something called model predictive spread control approach also, where the control is parameterized in the form of a kind of polynomial expression, let's say. So if you parameterize that in something like a linear or quadratic thing like that, essentially it further reduces the dimensionality of the variable, free variables, and also guarantees control smoothness by enforcement actually. So utilizing this idea, we came up with, we put that this expression back into this error equation, and essentially we kind of constrain the freedom to the parameter freedom only basically. Then we told, okay, we can formulate a parameter optimization problem in the framework of S and V's, and then get a quick solutions from that side of the story actually. And then the same idea can be done for quadratic problems also. And this quadratic formulation du case done that way, okay, the errors in ABC, and then you can come up with this constraint equation. Now the question is, if it is a square equation, that means you have something like 3 constraints and 3 variables, then you can directly solve it, okay, like this. But if you have only 2 constraints and you have 3 freedoms like that, you can actually talk about some optimization also. And this optimization, if you select a quadratic function like that in the set of parameters, and there are then it leads to this fast computation of this in closed form also. So very quickly you can update these parameters and proceed further actually. Okay, so that's the idea of spread control, and we have given good real life example problems of missile guidance and all that as part of the lectures in this course actually. Okay. Alright, then we went ahead and thought about putting this very recent idea that one of my students have proposed in his PhD actually. There's something called generalized model predictive static programming, generalized MPSP actually. Alright, so if that is the whole idea that somehow we don't want to start with discretization basically. We want to do all the things, all the algebra in the continuous time framework itself. Then the formulation doesn't demand that you start with a discretization. So you start with the original system dynamics in continuous time, okay, and you have this output also in continuous time. The whole idea is at t goes to tf, y of tf should go to y star of tf actually. Then an analysis of this output error essentially ended up with some expression like this. The details are there in the lectures actually. You can see the corresponding lecture, you can find that. Then if you have this, then this b of t has to be computed. Okay, this is sensitivity kind of time varying sensitivity matrix actually, and that can be computed like this. Okay, B of t is nothing but W times this one, where W of t can be computed backwards with this final boundary condition turns out to be like this, and W dot turns out to be like this. So, you start with this final boundary condition and backward integrate it from Tf to T naught, then evaluate this V of t all over actually. Okay, so if you do that, essentially it is kind of very close to MPSP, but it generalizes that, so that you do not get confined to very kind of discrete formulation and all that actually. Okay, so the idea here is, again you can have you can formulate a quadratic cost function in control variable for minimization, subject to this constraint equation now. Okay, and how this equation came and all, I encourage you to see my other lectures for details actually. Okay, then if you want to solve this parameter this optimization problem what you see here, then essentially you have to have this remember this not necessarily we are talking about like a parameter optimization problem here. You are still talking about something like a integral function minimization and all that actually. Okay. So, you have this augmented cost function which is like this, but still this is algebraic constraint, it is not a differential constraint, remember that. So, this constraint comes outside the integral actually, and then utilizing the necessary conditions of optimality that way, we will end up with some expressions this way actually, these two expressions for which we need to solve for this control and all that. So, that can be solved. So, we start with this and that. So, you can substitute this expression and solve for lambda, then back substitute here and get this delta us actually. Alright, so the control update happens to be in this form where lambda can be evaluated that way. Okay. Alright, so that was the generic MPSP ideas and all that actually. So, these are all various optimal control ideas that we talked about, and a little more further towards the end also we talk control constraint problems and all that again back in the control design. But at that point of time, after discussing this concept, we thought okay, we will go back to the estimation side of the story and have this ideas on estimation as well. So, we started with LQ observer design, and we said okay, if the system is linear and we have this sensor output vector something like this, then we can fit an error observer dynamics like that. The difference between this and that is this term, where this is a actual output from the sensor and this is a predicted output sort of thing. So, if you take the difference and augment this in the observer dynamics, okay, and especially if we design K in a smart way, in a good way, then the error that is x tilde is x minus x hat, this error will go to 0 asymptotically actually. Okay, that is the whole idea of observer design. So, then we analyze these two ideas, one is control design, one the observer design. This happens to be very close to each other. So, the only problem is okay, here the gain matrix appears right, whereas this gain matrix appears left here actually. So, to avoid this, we observe that okay, we can excite this eigenvalue concept. So, eigenvalue of any matrix is any matrix is same as the eigenvalues of its transpose. So, utilizing that fact, we can write it something like this, and then we can now correspond to this observer to control formulas and all that. And finally, we can have this concept of system versus dual systems, and one is controllable, the other is observable, one is observable, the other is controllable. That kind of ideas we can excite. And because we know the LQR design, the final results, we can actually come up with observer designs also, which talks about KE transpose, and KE transpose is given something like that, and hence KE will be given as something like transpose of this entire thing. Okay, so that is how the design is, and where this is the Riccati equation for the control design, whereas this becomes the Riccati equation for the observer design actually. So, this is called observer Riccati equation and all that actually. And also remember that this actually happens to be a kind of continuous Kalman filter, or Kalman filter gives us much more tuning capability, whereas this observer technique is a filter, but it does not give us that much flexibility for tuning actually. Okay, that is the only difference there. Then we went ahead and discussed some probability theory, random variables and all that to get ourselves ready for Kalman filter, and then finally switched over to went towards Kalman filter design and saw the derivations in detail actually. So, that is the problem here. We have this system dynamics, x dot is x plus v plus gw, and the measured output is something like cx plus v, and here now gw, that means w is a process noise and v is a sensor noise, they are now start appearing in the system dynamics itself. And we are assuming the variety of things, that initial condition and the process noise and sensor noise are given by these characteristics, and especially the process noise and sensor noise are zero mean white noise actually essentially. And we also tell they are mutually orthogonal. That means, if you take cross covariance matrix and all that, they will turn out to be 0 actually. And then the whole idea is to define this error between actual state and estimated state, and then we define the covariance matrix, something like x tilde times x tilde transpose, expected value of that, okay, as limit t tends to infinity. Okay. The whole idea is somehow we have to find this x set such that this error, this covariance matrix has to be minimized actually. And we had a lot of algebra analysis and all that. So, finally, it gives us something like this. We have to initialize with some guess value, and then it ends up with this filter Ricard equation in this form, very close to observer equation. You know that if you see this observer equation here, okay, and then if you see this filter equation here, it is very close. Only this G times G transpose is not there before actually. Okay, so that now it will, this process noise influence matrix, whatever this comes here, it will start appearing explicitly actually. Okay. Alright, so that is our continuous time convolutional filter. Once you solve this Ricard equation, filter Ricard equation, we have this gain computation that way, and you can propagate the filter dynamics like this, and y happens to be the measurement error, and Cx hat is nothing but the predicted output sort of thing. So, this error is also called innovation and all that way. Alright, so if you propose, I mean, if we continue to operate it from initialized state, and for linear system, it is guaranteed to converge by the way. Ultimately, this error will go to 0, and hence x hat of t will be a good representation of x of t actually. So, that is the whole idea of convolutional filter design. Okay. Now, we extended that for time varying systems now. Now, how do you do that and all that? So, they are now instead of constant matrices, this A, B, C, all that are time varying matrices now. So, how do you do about that? The assumptions were fairly similar. We had this process noise and sensor noise here, and those both of them are assumed to be 0 mean white noise all the time. Then initial condition, process noise and sensor noise, they are all assumed to be mutually orthogonal. And then we have this W and WT and VT are uncorrelated, non-stationary white noise actually, we assume that kind of a thing. And these expected values happens to be correlated, white because of these conditions actually. Take expected value of W transpose, they are the Q only when t is equal to tau sort of thing. If tau is not equal to t, they are 0 actually that way. So, utilizing that now there is no guarantee that this matrix Ricard equation will there is nothing called matrix Ricard equation now. So, we have this P dot equal to the differential Ricardi matrix, what I mean. Now, the idea is, okay, if P cannot be minimized, then can we at least minimize P dot actually, okay. So, then that leads us to the idea of selecting this cost function to minimize trace of P dot, essentially a norm of P dot actually. Then the solution happens to be like this. If I evaluate this partial derivative del j by del k, that has to be equal to 0, and then this expression gives us that k is nothing but that actually, very close to what we have before. But the Ricard equation is no more stationary. This is not equal to 0, but is equal to P dot actually now. Okay, so, we start with some P dot, P naught, some guess value for P, then propagate this P dot equation. Okay, remember the nice thing about filtering theory, everything is propagated forward actually. Okay, nothing like control theory, something is Ricard equation is solved backwards and things like that. But here, because of dual system properties and all that, it turns out that even Ricard equation you have to propagate forward only actually. Okay. Alright, so we have to propagate P of t starting with this initial condition and using this equation, and then every point of time we can compute a Kalman gain, which is actually time varying, and then use that in the filter dynamics or observer dynamics actually. Okay. Then we had this discrete time Kalman filter, okay, DKF sort of thing. Essentially, the summary is like this: we have a discrete time, complete discrete time formulation. Okay, so we have to initialize the state and initialize the covariance matrix also. Then you compute the gain this way. Okay. Okay, and then we have this update. Okay, once you compute the gain, you can update the state to the next time step actually, at the same time step, and then you can update the pk also, okay, at the same time step. See, this minus plus notations was necessary because the minus is something that either you start from the guess value or you kind of propagate there from the previous value. But once the measurement value keeps coming, at that point of time your gain is ready, so we can actually update the values depending on the measurement error actually here. Okay, error between the actual measurement and predicted measurement, whatever is the error, that will help us in giving a different value compared to this minus actually. Okay. Similarly, the covariance matrix needs to be updated also, and then once these values are updated, then you again propagate it using this noise free system dynamics like this actually. Then we had the whole motivation of continuous time, discrete time and everything is the fact that we are actually interested in continuous discrete Kalman filter. That means the system dynamics is continuous, but the process the sensor output are actually discrete. So, in that setting what happens actually. So, that is where the idea comes. So, that okay, I start with some guess value T naught, but I can propagate in a much better way, like utilizing higher order numerical methods for integrating continuous time systems. And then I will end up with some predicted value, and there when the output comes, when the sensor output comes, I can update that, and then I can keep on predicting until the next sensor output comes at T2, and then update, then continue like that actually. So, that's the for prediction part we want continuous system dynamics in a continuous time of framework, but for updating we know the sensor cannot be continuous, sensor output cannot be continuous, it can come only a discrete time, discrete points of time. So, the prediction becomes continuous, whereas update becomes discrete actually. Okay. So, in that setting the result turns out to be like this. We have this model, okay, which is actually a continuous time state equation, linear still, okay, and then we have this discrete time output equation. So, we initialize this again with some values x hat of 0 and p0 minus, these two values have to be initialized, and then we compute the gain. And then when the measurement comes, we update it in the discrete time setting actually, discrete time result sort of thing. Okay. Okay. Now, you can update the covariance matrix both ways, but again it is always preferable to use this to avoid the extra difficulties actually, even though this expression turns out to be quite kind of simplified compared to that, but this retains this the symmetric properties and all that actually. Okay. So, that it is still advisable to use this expression instead of this expression actually. Anyway, so the propagation again after update you can have to propagate, and propagation can be done this way. The only difference is this additional nonlinear term of P is not here. Okay, that happens because the output is not continuous and hence it does not get correlated in that sense. Okay. Anyway, finally, there was an idea that all this we studied because of understanding this so called EKF or extended Kalman filter. That is what it is used in practice heavily actually. So, here the system dynamics is nonlinear, okay, and the output equation is also nonlinear. So, then we have this idea of continuous EKF, in the sense that system dynamics is continuous and output is also continuous. But if you can generalize that and tell okay, we can also have continuous discrete formulation where the system dynamics is continuous, whereas the output is actually discrete. Okay. Alright, so the initialization again the procedure is fairly similar. Again, I don't want to derive and explain and all that here in this last lecture actually, but I hope all of us have done that actually. So, essentially the idea is you can linearize these two nonlinear equations about the current value of the state, and then you can utilize the Kalman filter theory for the corresponding linearized problem actually. That is the whole philosophy there. So, the operation happens to be like this. You start with the initial guess value for the state and initial guess value for covariance also, covariance matrix. Then you compute the gain. Okay. Then you can propagate the system dynamics. Okay, as well as the Riccati matrix. In these two equations actually. Okay. Now, eventually the continuous discrete EKF. That is what we need. The system dynamics happens to be continuous, whereas the output happens to be discrete. In that setting, there is a mixture of ideas actually. So, we again have to initialize this and then compute the gain at every point of time, okay, that way, and then update. Okay, as soon as the measurement comes, we invoke the discrete relationship and update that, and then after we are done with update, we can predict it or go for propagation mode using the continuous time theory actually. Okay. Once again, the nonlinear term is not there because the measurement happens to be discrete. That is the reason actually. Alright. So, after studying Kalman filters, we also had a glimpse of what is called LQG design, okay, in the setting of linear control theory again. So, essentially the philosophy was you have this LQ controller or rather LQR controller and LQ estimator or Kalman filter in the loop actually. Okay. So, if you put both the things together, then that is something called LQG design actually. Okay. Essentially, you are using the control formula for LQR, but the state u equal to minus kx, but instead of that you are telling u equal to minus kx hat. So, x hat is nothing but the estimated state actually, that sense basically. Alright, so this is what it is written. Instead of u equal to minus kx, you use minus kx hat actually. Okay. And justification comes from the fact of something called separation principle, which tells us that these two things designs can be actually done independently without harming the closed loop behavior. Essentially, if you see that analysis, tells you that the closed loop, the closed loop system dynamics and the error dynamics, if you sell the eigenvalues of both the things and then put them together and analyze the eigenvalues, they don't get altered actually. So, in other words, they happen to be kind of separate actually. So that's the basis of this LQZ design. But remember, that is valid only for linear systems actually. Okay, even though people do that for nonlinear system, there is no proof per se actually for nonlinear systems in general. Okay, so towards the end, we also discussed something called control constraint optimal control in detail. So, we went back to the objective and tell, okay, we start with the same objective, whatever the regular control optimal control is supposed to do, means to find an admissible time history of the control in this region, so that it causes the system governed by this system dynamics to follow an admissible trajectory, and on the way it should optimize a cost function, it should satisfy the boundary condition as well, but at the same time it should be confined to a set. That means control is not really infinity, it is actually confined to allowable limits actually, or component wise they can be restricted between some minimum value and maximum value sort of things actually. So, if you do that, essentially this is a great contribution from Padhi, and it tells us, essentially it tells us that, okay, the regular theory can be used, you can still define the Hamiltonian that way and carry out the necessary conditions of optimality. The only difference is the optimal control equation. So, instead of del s by del u equal to 0 and try to solve the control out of that, you have to all carefully analyze this relationship. That means, Hamiltonian expression evaluated for optimal control has to be less than equal to that same expression evaluated for a non-optimal control. And utilizing this relationship carefully, you should be able to kind of come up with some sort of a control function actually. And this equation has to be honored also, by the way. This state co-state and boundary condition has to be honored also on the way basically. Okay. So, topics that we studied in detail talks about Padhi minimum principle, some sort of a cursory proof is also there, the idea behind how it comes, how we will end up with that actually. And then we actually talk about a great deal of analysis for time optimal control system, the minimum time control problem, and we have been taken a double integral system to demonstrate the idea in fair detail actually. We essentially come up with the switching control sort of ideas, we define some sort of a kind of switching function and then switching regions and things like that. And we told, okay, it can be, control can take a discontinuous sort of, one time it can be discontinuous, but with some sort of appropriate switching at appropriate time, we should be able to do the job and drive the system towards origin, even if the control is constrained actually. Yeah. Then we also studied energy optimal control for LTI systems in general, okay, where things were much more benign compared to this time optimal control. And on the way, I also told that there is another concept called fuel optimization problems, and which was left out for self-study actually. Okay. So, both this time optimal control and fuel optimal control leads to this singular arc, this discontinuous control or singular arc problems like that. Whereas, the energy optimal control, where you want to minimize something like a quadratic cost function of control variable, is much more benign, and it naturally leads to something that we feel intuitive actually. In other words, as long as the control is away from the bound, then you apply the regular value, and the moment it goes away from the bound, you apply the bound value actually. Okay, and that is possible only when we have this nice formulation of quadratic cost function in control variable and all that. It's called energy optimal control actually. Okay, so details you can see that in the lectures, and you can study the corresponding books also basically. Okay. Then towards end, we also talked about state constrained optimal control. That means need not be only control constrained, inequality can come in state variable also. There we studied two methods. So, one was the penalty function approach, where we had this problem like this. We have the system dynamics like this, and performance index was given like that, but also had a bunch of inequality constraints as functions like G1 to Gp actually that way. Okay. So, we assume that the constraints are smooth, in other words, they have this continuous first and second order partial derivatives and things like that. Then the whole idea here is to formulate an auxiliary state equation. So, xn plus 1 dot is something like this, something like a quadratic functions times a Heaviside function now, h of g1 and up to gp, is exactly similar way, where this Heaviside step function is defined something like this. If it satisfies the constraint, it is 0, that's not active, but if it doesn't satisfy, this becomes 1, that means this function is suddenly active actually. But the critical observation was, like, we are not only this state equation, along with the state equation, we want to put this boundary condition also. That means, this equation which is guaranteed to be positive, the moment any of the constraint is not satisfied, the x dot is guaranteed to be positive, and hence this boundary condition will never be met together basically. So, essentially it tells you that, okay, this formulation makes it some sort of an infeasible problem unless all constraints are satisfied actually. Okay. So, now the idea is, okay, I will take the original problem as it is, but I will augment that with this state equation and this boundary condition as well. So, essentially I will solve some sort of artificial problem which talks about problem in n plus 2 dimensional space actually. So, that was done. I mean, that's one idea basically. The other idea we talked about is also slack variable method, and in my personal view this is kind of better than the other one. And here the problem was again revisited in a little more generic sense. This terminal penalty is also there here, but that can also be there in the other formulation. I mean, that's not a restriction per se. The idea here is, okay, we have these constraints, okay, given something like this. So, then we wanted to formulate this equality constraint out of this inequality by introducing this half alpha square. Okay, remember this is a scalar constraint. So, if you have multiple constraints, you have to do multiple times all these tricks actually. So, if you have scalar constraint like this, you can have this equality constraint now. But remember, going back to the static optimization problem, where we kind of did the similar thing while deriving KKT conditions. But here, the idea here is to not to neglect the value of the slack variable, but actually to compute the slack variable and its derivatives together actually. Okay. So, to do that, there was an observation that this equality constraint, if I take a derivative, this leads to that. If I take subsequent derivatives of the same expression, ultimately I will end up with some equation like that. But also remember, this assumes that this polynomial is of pth order. That means, if you take pth order derivative of this polynomial, then control u appears explicitly basically. Okay. So, that is the utilizing that fact. So, from this expression I can actually solve for the control, okay, in terms of other variables. Okay. So, the last derivative, that pth order derivative equal to 0, if I utilize that thing, then I should be able to solve control in terms of other variables actually. Now, once I do that, I can revisit the state equation and I put, okay, state equation is nothing but f of x u, but u is now something like this. So, I put it there here, and in this I will consider alpha p as control, but all other things as states actually. So, I should be able to augment these state equations also, which is very much straightforward actually. Okay. Alpha dot is alpha 1, alpha 1 dot is alpha 2, like that actually I will be able to do that. Well, alpha p happens to be a control variable, and the fact is alpha p is actually unconstrained also. So, the same constraint has been taken care in this equation itself. So, alpha p, it turns out to be unconstrained actually. So, again, we add a kind of p states to the n states. In other words, we increase the state dimensionality, but ultimately we are able to kind of convert a constraint optimization to a free optimization problem actually. Now, if you introduce the state equation, we also need a bunch of initial conditions for that, and that was fortunately it is possible to solve for the initial conditions as a function of the initial conditions for the state n time actually. Okay. So, utilizing this equation, you can actually solve this alpha of t0, alpha 1 of t0 and things like that. So, this formulation is kind of very compatible in that sense actually. So, again the formulation takes a little bit higher dimensional, but essentially ends up with a free optimization problem when alpha p is considered as a control variable actually. So, that was given there, and you can actually go ahead and solve this problem that way. So, these are the two methods that we kind of discussed as part of the state control, state constraint optimization problem actually. Now, towards the very end of this course, we also thought, okay, we can extend the scope of this optimal control to the distributed parameter systems as well. And distributed parameter systems by nature are governed by partial differential equation, which is very different from whatever we have seen so far actually. But there are many examples where we have to talk about partial differential equation. And, for example, heat transfer process, fluid flows, chemical reactor process, and vibration of structures, and then ecological problems. Many things are there where ODEs are not sufficient actually. So, how do you handle with those kind of problems actually? Now, going back and seeing what can be done for this distributed parameter system, there are two approaches. One thing is kind of design and then approximate. That is what mathematicians will love to do that. They invoke this infinite dimensional operator theory and do all sort of nice algebra there, and then finally come up with the control expression. Then they discretize it ultimately and then try to implement. So, that is kind of design then approximate. But the engineering approach follows a little bit reverse way. It find out, first of all, it does approximation and then does the design actually for that approximate problem. And that way it can be done two ways actually. One is design without model reduction, which is not very much advisable, because you really end up with a large number of grid points again actually. Okay, but then you can also utilize the concept of design with model reduction. That means not only you approximate that system, but you introduce the system kind of model order reduction sort of ideas there, and they come up with a lower dimensional representation of the same thing, and then utilizing that lower dimensional system, you can design a control system actually. So, that is the idea of design with model reduction actually. Then the various topics that we covered under that in relatively fair detail is something like this. First, we started with the idea of putting finite difference, and then utilize the same idea of LQR for linear distributed parameter systems actually. And we gave some examples also to demonstrate the idea there. Then we took a little digression after that, where we talked about optimal dynamic inversion. Okay, and then that was done by utilizing this continuous actuator and a set of discrete actuators subsequently actually. It is actually not very much in the framework of variational calculus and all that, but I still thought it is a nice idea to discuss about. Okay, variational calculus is used, but not in the framework of what optimal control framework would like to do actually in a way. In other words, we had this quadratic error quantity, and then quadratic error was actually enforced to go to 0 utilizing the dynamic inversion ideas there, where you enforce this stable linear error dynamics and all that, but that will give us only a constraint with infinite freedom. So, there is the scope for getting this calculus of variation a little bit, and then we solve for controls assuming both continuous actuator, and also subsequently we had this discrete actuator formulation and all that, where this control singularity starts coming as the objective starts getting met actually. So, there was a necessity of switching over, and they are having some two goals, one in the beginning, one towards the end, like that actually. We demonstrated that utilizing examples also basically. And also we had this single network adaptive critic based optimal control formulation, and that we thought we can directly do that utilizing only directly finite difference, and then putting the grid points and then solving the problem on the grid points only. But you can also have this idea of invoking this model reduction through this basis functions design using this proper orthogonal decomposition sort of ideas, where you can start with something like a set of snapshot solutions, and utilizing the snapshot solutions you can actually design basis functions which are tailor made to that particular problem, and utilizing those basis functions you can actually come up with those basis functions needs to be utilized in Galerkin approximation to come up with something like a low dimensional ODE representation of the system dynamics, and then utilizing that ODE in the model form. You can actually come up with something like a state feedback control design actually. So, that details of that can be seen in the particular lecture basically. We have also given examples on the way basically. Alright, so finally at the end of the course there are some concluding remarks. First remark is a variety of difficult real life problems can be actually formulated in the framework of optimal control. Do not forget that. Okay. And incorporation of optimal control issues leads to a variety of advantages, like you can talk about minimum cost, minimum time, or whatever maximum efficiency or non-conservative design, things like that. So, optimal control framework gives us a very good platform, very good tool actually for doing that. Okay, and then modern techniques are capable of addressing the fundamental issue of what optimal control theory was kind of suffering from for a long time, and that is nothing but computational complexity. So, computational complexity, various good algorithms have come up and then are still developed actually, and in that sense it is a resource for doing a good research also actually. But having said that, there are many techniques available like pseudospectral method, MPSP, SDRE techniques like that, which actually kind of tries to address this computational complexity issue in some sense basically, and then this computational advantage coming from the computer side That means the computational power is increasing day by day. That also helps actually. So it doesn't make sense to kind of get confined to the old idea that okay, optimal control cannot be used in real time. It can be actually. Okay. And in this particular course, we discussed a variety of classical and advanced optimal control techniques, both in the setting of linear and nonlinear framework actually. Okay. So both have been covered in this course also basically. Now coming to the estimation theory part of it, also remember that's a very good complement for the control design part of it. And state feedback control designs needs the state information for control computation. That's the first thing why we want to study estimation theory actually. And estimation theory, once you know, it enables the optimal control or any other state feedback control design in a very good way actually. So don't forget that part of it. That's a good motivation for us to study estimation theory. Then sometimes we need auxiliary information like the target information, obstacle information like that for coming up with strategies. That means guidance strategies and things like that. For that, we need to have target estimation, obstacle estimation or things like that, which is not the states of the own vehicle or own system, but the states of the other system, which is necessary for doing some computation on our own system actually. So for that also we need estimation theory. So many other applications are also there, like something like parameter identification, fault diagnosis and many things like that, where if you know estimation theory in a good way, then it enables you in a very good way actually that way. And nonlinear estimation theory is a kind of a nice combination of scientific as well as heuristic thoughts. So for example, like extended Kalman filter, even though there is no theoretical guarantee, but we know that it works very well. But it has difficulties in tuning also. So tuning part you can put it into heuristic or experience sort of thing. But once it starts working, it works in a very good way. Finally, Kalman filtering, which is kind of most commonly used in practice, has been covered in this course in detail. And both basic fundamentals as well as advanced topics, something like EKF, even some little bit kind of UKF ideas and all we have also discussed actually. So you can go back and study this course in a good way. If you if you don't understand, it take your time, and there will be practice problems on the way. Try to kind of solve those problems, get a better understanding. Now that after going through the course, I am confident that you can also be able to read many books and then enrich your knowledge further actually. So with that, let me sign off from this course. Thank you and goodbye.